There we go. Now it's rolling. Jalen, hello. We are going to do 4-8. I don't know if we'll get done with this today. There's a lot of examples. Yeah, we'll see. We'll see how far we get. But Rolle's theorem, mean value theorem, I think we've actually done this before. We've actually talked Rolle's theorem, mean value theorem briefly in the past, okay? So, here's in a nutshell, here's the deal. Ready? Rolle's theorem, mean value theorem. What they're going to do is they're going to focus on the endpoint. So the left endpoint, right endpoint. And what's true for Rolle's theorem? I'm going to draw a little arrow. For Rolle's theorem, here's what's going to happen. Your left and right endpoint are going to be exactly across from each other, meaning they have the same y coordinates. So whatever the x coordinate is, let's say this is something, comma, 4, and this is something else, comma, 4, right? They are directly across from each other. They have the same y coordinate. Great. Okay. What this is going to say is that if I have a function that's connecting those, right? Connecting those dots. So I have a line that's between those dots that is continuous, meaning no jumps, no holes, no skips, no vertical asymptotes, no any weird things happening.
No piece
And it's differentiable, which means it's not just a straight line going all the way across. Okay? I can take the derivative of it. That means that there must be a hump or a bump at some point, right? Maybe there's two humps or bumps. So maybe it looks like this, right? What they're saying is that at some point there has to be a horizontal asymptote because the slope between these two guys, the slope here is 0. So there has to be a place somewhere where the slope is also 0, right? Now maybe he looks a little bit different. Maybe he's here and here and I have this going on, right? In which case the slope from here to here, where my start and my end point are, the slope between my start and my end point is 0. I have a slope here that is 0, and I also have a slope here that is 0. What we're trying to do is we're trying to find the place where the slopes are zeros, which means like the high and low points. This is called Rolle's theorem. R-O-L-L-E-S theorem. Okay, we take the start and the end point. We find that those two are exactly horizontal from one another, and then find another place where the tangent line is horizontal. So what we're going to do is we're going to take the derivative, set it equal to 0 to find this place, right? I want to know where the slope of the tangent line is 0. Okay. Next is something called the mean value theorem, which is essentially similar to Rolle's theorem, but here's the deal. Okay, ready, set, go. Instead of my endpoints being directly horizontal from one another, I'm going to make this really easy on you, okay? I'm going to say this is the point 1, 2, and this is the point, 4, 8, right? Okay? 4, 8. So here's the deal. There's going to be a function that is between these two. So let's say like my hump and my bump is looking like this. I don't know. Something like that, right? If I do the slope between these two guys, which is 8 minus 2 over 4 minus 1, which is 6 over 3, which is 2. Yeah? This guy, this line has a slope of 2. What this is saying is that there has to also be a place on this curve. I'm going to pick it right there because that looks about the same. There has to be a place on this curve where the slope is also 2. Similar to Rolle's theorem, except it's just not 0, right? I actually have a slope, a number that's other than 0, okay? This is called the mean value theorem. So difference between Rolle's theorem and mean value theorem. One of them, they're both saying the same thing. They're both starting from the slope between the endpoints and then saying there's another place between those two that also has that same slope. It's just in Rolle's theorem, the slope is 0. In the mean value theorem, it's some number other than 0, right? Where they're like slanted lines. Got it? That's how that works. Rolle's theorem, mean value theorem. So here's the deal. Rolle's theorem, here's some other pictures. So I have these two that are directly horizontal from one another. So when I do the slope of those guys, that slope is 0. I want to find the place where the slope is also 0. Okay? Same thing over here. A and B are also, if I draw a line between those two, they will have a slope of 0. Here I have two places where the slope is 0. That guy has a horizontal tangent line. This guy has a horizontal tangent line. Now, how do we find those places where the tangent line equals 0? Where the slope of the tangent line equals 0. What is slope of tangent line?
Derivative.
Derivative. So I'm finding where the derivative equals 0, or in other words, finding the critical numbers.
Of the first derivative?
What? Of the first derivative. First derivative. Yep. Because we're just trying to find the humps and bumps. So I'm just taking the first derivative, setting it equal to 0 to find where those horizontal tangent lines are. That's all.
So we take derivative is equal to
The slope of the tangent line.
So how the heck is this different?
Wait, the
Not really, it just has a name.
equal to the wait, hang on.
Because we'll do a story problem with the mean value theorem. That's kind of fun here in a little bit. That's like proving why somebody is speeding. Okay, what?
So do we set the derivative equal to the slope of the tangent line?
No,
or
the
slope
derivative
of the tangent line
is the slope of the
same?
tangent line.
Okay.
Yeah. Yeah. So we set the derivative equal to 0 to find those humps and bumps. Okay? All right, now, the hardest part of this is going to be like, what the heck are they asking me to do? So I'm going to read this through really slowly. Eli, are you with me? Eli, are you with me? Come on. Do you have these notes? Yeah. Let's go. All right, example 1. It says, find the two x-intercepts. There are two x-intercepts of this guy. How do I do that? How do I find x-intercepts?
Equals 0.
Plug 0 in for y. 0 in for y, and I solve. So I'm going to plug 0 in for y. I'm not reading any further other than to just do this part. Okay? 0 in for y to find the x-intercept.
Would be x. No.
He's a simple trinomial. Multiply to get 4, add to get 5. Negative 5.
Oh, negative 4 and negative.
Negative 4, negative 1.
Yeah.
Which means x equals 4 and x equals 1. If those are my two x-intercepts, right here and right here, are they across from each other?
No.
Like, are they horizontal with one another?
They
1 and
can,
4?
yeah.
Those are my x-intercepts?
Yeah.
Yeah, they're straight across from one another, right?
X
So if I were to
y.
draw a line between them, the slope would be
0.
0. Okay, it says, so I find the two x-intercepts of the function, blah, blah, blah. We are at this point and we are done with that, right? We found the two x-intercepts. They are 4 and 1. Then it says, confirm that f prime of c equals 0. What does this mean? What is f prime of c?
Find the critical numbers.
Derivative.
Show that the derivative equals 0 at some point between those two.
Okay.
Okay, so let's do the derivative. What's the derivative of this guy?
2x,
Minus 5. If I set him equal to 0,
plus 5.
I add the 5.
Divide by 2.
Divide by 2.
X equals 2.5.
2.5. He is going to have a horizontal tangent line at 2.5, just like it says in the graph, right? 2.5, and does 2.5 live between my two intercepts?
Yeah.
Yes, that is what Rolle's theorem says. It says that if I have 2 points that are exactly horizontal from one another, there will be a hump or a bump between them.
Is that all?
That's what Rolle's theorem says. Yeah, that's not too bad, right?
I can do that part.
Yeah.
I don't have to do anymore.
Okay.
No, we got the absolute
Okay.
value.
What?
See an
He has a
absolute
tippity
value?
tip. We can't do it.
Yeah, he's got a tippity tip.
He does have a tippity tip.
We're kicking him out. We're giving him the boot.
Mhm.
I don't
Yep,
know.
yep. All right. The differentiability requirement in Rolle's theorem is critical. So, our function has to be differentiable at all points between the two values I'm looking at.
We can't.
So, if they were asking for this guy and like this guy, and I'm looking at just this interval from here to here, that's okay. Because the tippity tip doesn't lie in my interval, right? But if we're going from -1 to +1, we're going to have a problem because you can't find the derivative at this point right here because he's a tippity tip. Okay, so that's where they say the first sentence says the differentiability requirement in Rolle's theorem is critical. If my function fails to be differentiable at even one place on the interval, if it's not in the interval, it's fine. But if it is in the interval, we cannot use Rolle's theorem. Rolle's theorem does not apply, or the conclusion of the theorem may not hold. For example, the function absolute value of x minus 1 has a tippity tip. He has roots that are -1 and +1, which are these guys here. So that's where I would probably be looking at. My slope between those two is 0. Great. I want to find a place between those two that also has a slope of 0, except he is not differentiable here. No deriv here. Therefore, Rolle's theorem does not apply.
Okay, so what if it's like -1 to 0? Like if it's, how does that work?
If you're going -1 to 0, so if you're going from here to here, For one thing, you couldn't use Rolle's theorem because they have to be horizontal from one another. But you could do the mean value theorem on there. Yes, you could. Because technically you can find the derivative here. Now, if I'm looking at that, so this is an interesting question and it kind of has a loaded answer. Are you ready for this? Okay. So this dot and this dot, if I was specifically looking at between those two, I could apply the mean value theorem, right? It's just the slope between those two is -1. I want to know where it also is going to have a slope of -1. Everywhere between those two. Right. So this one will have infinite answers because every place in between those two is going to have a slope of -1. Yes. Right. And what will happen is this guy right here, okay, so the original function is the absolute value of x minus 1. This is an interesting way of looking at absolute value. This side of the graph is -x minus 1. True?
Yeah.
This side of the graph is positive x minus 1. Those are two linear functions, one looking at the left half of the v, one looking at the right half of the v. If I take the derivative of the left half of the v, what do you get?
-1.
-1, which means he's -1 everywhere for us derivative. His derivative is -1 everywhere. Makes sense, right? Yeah, that was a good question to ask. I like that question. So, again, you could do mean value theorem if it was just from the interval from here to here, but we can't do it overlapping 0 because he's got a tippity tip. Got it? Okay. Let's go to the next one, example 3. Here is one for sine. Y equals sine of x. Okay?
No ants.
Yeah.
I like this lesson.
Yeah, Comey, no ants.
No ants. I'm sorry. I'm not going to do ants. Okay, I won't do ants. All right. If f satisfies the condition of Rolle's theorem from A to B, then the theorem guarantees the existence of at least one point. Ugh. There might be more than 1 point. So, an example, if my interval is going from 0 to 2 pi, because we're doing with sine, we're in radians, right? We're going from 0 to 2 pi, so my interval is 0 to 2 pi. And we do have another place in there that is 0, but we don't really care. The slope between my starting and ending points would be 0, so there has to be at least one place where the slope is also 0. In this case, there are 2 of them where the slope is also 0. So, what we want to do is, how do we find those 2 places?
Take the derivative, but I don't remember.
Take the derivative. What's the derivative of sine of x?
Wait, isn't it just cosine?
Cosine. What's the derivative of cosine?
Negative sign.
Negative sign. Yep. So y prime equals cosine of x, and I want to set him equal to 0. So I want to find where cosine is 0 between 0 and 2 pi, right? Okay. Cosine is 0 at a lot of places. If you want to look at your unit circle, you can. But cosine starts at, he looks like this. He starts here and he goes down and he comes back up, right?
Yeah.
So 2 pi is here. 1 pi is right here. Here is at pi over 2. Here is at 3 pi over 2. So he is hitting 0 at pi over 2 and 3 pi over 2. Do you see that? Which means that this graph will hit a horizontal tangent line at pi over 2 and 3 pi over 2.
2 and pi over 3.
3 pi over 2. 3 pi over 2 is like 1.5 pies.
These make sense.
I would like
Yeah,
two
we
full
don't
size
mind
things. I would like
those.
chocolate and cherry.
See, I'm not a cherry pie eater. Peach
No?
and apple, that's where it's at. Or cheesecake. I
I'm
mean,
like not a pie.
if
person
that's
in
an
general.
option.
I don't know why.
I
You're
just
not a
like
pie
all
person?
good
Well, I guess I
foods.
like pecan pie.
Pecan pie? See, I'm
I
not a
like
pecan pie
fruits.
eater.
Anything
Okay.
with fruit, like kolaches or pies or cheesecakes.
Nice. Yeah. So this example is here to show you that there may be more than 1 point where he has a horizontal tangent line. Whatever. Okay, mean value theorem is the same as Rolle's theorem. It's just that this guy and this guy are not going to be horizontal from one another. So you have to do one extra step, and that is finding the slope first, right? And they do weird things when they say the slope. They call this guy the slope. They say the slope is f of b minus f of a over b minus a. That is a fancy way of saying
Y2 minus Y1.
y2 minus y1 over x2 minus x1.
That's
Ooh,
stupid.
x2 minus x1. Blah, blah, blah. Okay, do you see how that works?
So we just
Now they say f prime of c, which means instead of taking your derivative and setting it equal to 0, you're taking your derivative and setting it equal to whatever the slope is.
Ah.
So like up here, instead of setting it equal to 0, we would set it equal to 2, which is what it was in that case, okay? So let's do an example. Oh, and then we might.
I actually
And-
like this lesson.
Yeah, this is not bad. And there could be more than one place where he has a slope of whatever that slope is, right? Okay,
Right.
just like with the hills and valleys, the bumps that we just
How do you
did.
determine what C1 and C2 are? Like, how do you determine, say, if
And those are
it's
just
one-
your two answers that you get. You might just get two answers.
Okay.
That's
But
what you
how do
get
you
when
know
you
what
said the
number it is?
That's what you get when you set the derivative equal to the slope.
Yeah.
Yeah.
Yeah. And it doesn't really matter which one you label as C1 and C2. Usually the left point is the C1 and the right one C2. So,
Okay.
all right. So let's go to example 4. Here we go. Show that the function, this is a cubic function, 1/4 x cubed, satisfies the hypothesis of the mean value theorem. So the deal here is that, over the interval from 0 to 2, we have to check that box off first. Does it satisfy the hypothesis of the mean value theorem? For one thing, is this function differentiable and continuous?
Yeah.
Maybe that's what we need to do. Diffable.
Diffable?
Is it diffable? Check. Meaning, can you take the derivative of this? Is this going to have any holes, any vase, any tippity tips, anything like that?
No.
No. Is it a continuous function? If it's continuous, does it have to be differentiable and vice versa?
No.
No, like a continuous, maybe we should check the continuous function box off first. Continuous means it can include tippity tips,
Oh yeah.
Right?
They connect, right?
okay?
To disconnect.
A continuous function includes tips, but a differentiable function then eliminates my tippity tips, right? Okay, because an absolute value function is continuous, right?
It's just not diffable.
It's just not differable. So, all of those boxes have checked. They're continuous and differentiable. And now, we're going from 0 to 2. So, we need to, first and foremost,
Plug in 0 and 2 to the equation.
plug in 0 and 2 and find my slope. So, 0 comma something,
1.
2 comma something. Okay? If I plug 0 in, 0 will be 0, 1, you said? Okay? If I plug 2 in, 2 cubed is 8.
3.
A third of 8 is 2.
Wait, why are we
2
plugging
plus
in
1 is
one?
3. What? We're not plugging in 1.
We're plugging in
We're
0.
plugging in 0 and we get 1.
We plug in 0, we get 1. We plug in 2, and we get 3 because those are the intervals on which we're looking at.
We're plugging into the original function, Jose, to try to find the y coordinate,
Oh,
right?
we don't
So we
know.
plug 0 in.
I thought we knew. It's on the graph.
Well, yeah, but we won't have the graph.
You know, we're not going to have the graph. That's
Yeah, I just give you the graph so that you can verify your answer.
Okay.
So 0, 1, and 2, 3. Now
minus 1.
we have to find the slope. So the slope of this line to connect those two is 3 minus 1 over 2 minus 0, which is 2 over 2, which is 1.
And then 3/4.
So this guy's slope is 1, and I want to find a place on this line that also has a slope of 1. So I'm going to do what now?
Find the derivative.
Find the derivative and set him equal to
1.
1. Yep, equal to 1. Okay, what's the derivative of 1/4 x cubed? 3/4 x squared, and the 1 goes away.
Equals 1.
That's my derivative. Okay, now what do I do?
Multiply 3/4 over.
I'm going to multiply by 4/3 times 4/3.
And then
That goes
square
away. X squared equals 4/3.
Square root.
I'm going to take the square root.
But we don't want a minus because we don't care.
And, okay, so technically, here we go. Technically, the answer is positive the square root of 4/3, right? Whatever that comes out to be, and negative square root of 4/3. Why do we not care about the negative square root of 4/3?
Over that interval.
Yeah, negative square root of 4/3 is over here, right here, probably like there somewhere, right? Okay, we're only looking at the interval between 0 and 2. Yeah. So he does have two places where he's going to have that tangent line, right? Like that tangent line of 1.
We just don't
It's just we don't care about this other one because we're only looking between 0 and 2. Yeah.
Wow.
So like, Josie, if you were looking at the interval from -2 to +2, you would have a C1 at negative square root of 4/3, and you would have a C2 at positive square root of 4/3. Yeah. So we don't care about this one. We just care about this one. Okay, and sometimes they'll write this as like 2 over the square root of 3, right? Like they'll square root the 4, right? Sometimes they'll write this as 2 square roots of 3 over 3. If you rationalize, do you guys remember rationalizing? Trig, you probably don't because we are going to get ready to do that
Yeah, I
here
remember
soon.
rationalizing.
You do remember or you don't?
I do.
You do? Yeah.
I hated it.
Uh-huh.
Yeah.
Yeah.
We've done that.
You have? You have? Okay.
Haven't we?
Yeah, we did that like in chapter R.
Yeah.
Yeah. We'll do that a lot this chapter because we're getting
Oh
ready
my
to do
gosh.
trig.
Yucky.
So anyway, there you go. So they might write the answer like that instead. All of those mean the same thing. Okay? Good? La 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 la. Oh, perfect. Okay, here we go. All right, I'm going to do my very best. I'm going to open up this book so I can get a graph here.
Tired. I need a nap.
We have
You're gonna
somebody that is driving on a highway. What?
Were you gonna make a straw graph?
You don't have to. I'm going to draw you a picture of what it looks like so we can like interpret this correctly. Okay? So, here we go. This is what we've got going on here. I think we've done this problem already actually in this class as well.
I don't think so.
Maybe, yes we have. It was like the speeding graph.
No.
Oh, he's not even on here.
Lizzie, what's the secret extra question gonna be?
I just know that speed is
Example
never
4,
enough.
example
You
5.
need it.
I don't even have a graph.
What?
Okay.
5 minutes.
Okay, so here's the deal. You are driving on a straight highway on which the speed limit is 55 miles per hour. Okay, here we go. We've got a bunch of weird things happening because they give this to me in miles per hour, but then they give me minutes. Like at 8:05, I'm going this far, and at 8:10, I'm going this far, which means 5 minutes. But we have to keep our units the same throughout. So if they give it to me in hours, I might have to convert to hours, or I might have to convert to minutes, whichever one. So keep that in mind. Help me remember that throughout this problem, okay?
Okay.
All right, a police car clocks your vehicle at 50 miles an hour. And at 8:10, let's see, a second police car posted 5 miles down the road clocks your velocity at 55 miles per hour. So, here's what I have going on here. I have at 8:05,
What's our speed?
let's
Did you not
go
find the graph?
at 8. I did not find the graph. I'm going to graph you one. Just wait a second. At 8:05, you're going how far?
55.
50. You're going 50 miles an hour at 8:05.
No, but that's just our speed. We have a velocity though.
Okay, the speed limit is 55. At 8:05, we're going 50 miles an hour. Okay, then at 8:10, we are going 55 miles an hour. Okay, so I am not speeding at any of those places in time. True?
Wait. Hold up.
But the problem is,
In between you're going.
check this out. This is 5 minutes in between, right? And I have gone 5 miles in 5 minutes. True?
That's a minute.
Which
Your
is
velocity.
Which is
means you
60 miles an hour.
on 55.
On average, right? 60
Right.
miles an hour is what it would have to average out to be, which means
Average.
I have to
Which means you
actually have been
went
gone
faster.
faster than that. So what was I going at a certain point in time?
70.
Let's figure that out.
75.
So to expedite this and to make this a little bit easier, let's say at a time of 0, I'm going 50. Okay? At a time of 0, I'm going 50. And then at 8:10, which is 5 minutes down the road, I'm going 55. Except, problem.
Except.
This is minutes. This is minutes. This is miles per hour. So, do we want to convert? Which one should we? Let's convert the minutes to hours. It's going to be ugly,
Fine.
but it'll be fine because it's going to make more sense when we look at it because we'll be able to see how fast we were actually going, like 75 miles an hour, versus going that many per minute. It's going to be like less than that, and you're not gonna have that in your brain. Okay, so even though it's gonna be ugly, let's convert. What's 5 minutes in hours
1/12.
terms? Yeah, this is 5 over 60, which is 1/12. Yeah, you're right. 5 over 60, 5 minutes out of 60 minutes is 1/12 of an hour. True? Okay, so this is what we have going on here. I'm only gonna do the first quadrant of the graph. I have at 50 miles an hour. I'm going at 0. This is 0, 50. 1/12 of a minute later, I'm just going to go over this much and I'm going to go up this much, right? I'm going 55. This is 50 miles an hour. This is 55 miles an hour. Yeah? Okay.
You said a 12th of a minute. I was very confused.
So this is 0 minutes, or 0 hours. Sorry, this is 0 hours. This is 1/12 of an hour. Okay, I'm just labeling that. All right. Now this says, the mean value theorem says, our function, when we are driving on the road, are we doing a continuous function?
No.
Are we continually driving?
Yes.
We're not stopping.
Well, yeah.
We're not, like, we might drive over a hole, but that
you
doesn't
can have
count.
a tippity tip. You can like stomp on the brakes real quick. Like,
Yeah, but we didn't. This is going to be a continuous function that's differentiable, right? So when we're talking about our speed here, like our velocity, okay? So at some point, I'm just going to draw it like this. Maybe I sped up and I did one of those, right? Like maybe it looks like that, where I started and I sped up really fast and then I went back down again. Like maybe it looks like that. Or maybe it's like right in the middle. I don't know. Like, I don't know what it looks like. Maybe I increased my speed and then all of a sudden I was like, oh crap, there's a cop up ahead. I don't know where this function is at, where I have the slope that's the same. Let's say it looks like this. I need to find my slope using mean value theorem. I need to find the slope of what this guy is from start to finish. And then I'm going to conclude that my slope has to also be that at some point in time, right?
We're working.
According to the mean value theorem.
Oh wait, no.
What?
I don't know.
Now, we have these 2 points. This is 1/12, comma 55, and this is 0, comma 50, yeah? So I need to find my slope. All right?
Y2 minus y1.
I'm going to go 55 minus 50 over 1/12 minus 0. Yeah? Okay, 55 minus 50 is 5 over 1/12, and if I want to keep flip,
60.
I'm going to multiply him up above. Is that 12? Yeah, multiply him by 12. Is that 60?
Why would his slope be 60?
Yeah.
Because
It is
you were
60.
going
Oh yeah, because your average is
5
duh. Because our average is that. Ah.
Because if you're going
Yeah, but that's not going to give me my
5
maximum
miles in
speed.
5 minutes, you'd have to be going 60.
Yeah, okay. So at some point I had to have been going 60. Whatever. But that's not my max speed,
No,
though.
because we have to find the derivative
It
now.
could be.
But the average.
No, it wouldn't. It would have to be, my max speed would have to be way higher than 60.
Maybe.
That's your average speed. Right?
To accommodate, like I was going 50 and then I was going 55. So I would have had to have exceeded 60 miles an hour
To raise the average.
to raise the average at some point. Anyway, whatever. It doesn't matter. It doesn't matter. So they can prove to me that at some point I'm going 60, right? According to this, since this slope is 60, and I'm going that in 5 minutes, yeah, 60 is what my slope would be. So they can prove basically that at some point in the middle I was going 60 miles an hour. Now, can we find exactly this? There's 5 miles down the road. Can I find exactly where that spot is located that I was hitting 60 miles an hour?
Derivative equals 60.
But I don't have a function.
We can make one.
No, we
No,
can't.
'cause you don't know.
We don't know. This is the problem. We don't know if I sped up right